You're having several lectures on various aspects of dark matter. And so today what I would like to say some complementary things and hopefully not repeat what Patty's already told you. And I would like to cover a few different mechanisms of dark matter production apart from just the thermal freeze-out one that he's been talking about for WIMPs, although I would like to also say a few more things about thermal freeze-out as well. So I'm going to talk about, in addition, asymmetric dark matter, freeze-in, primordial black holes from inflation, and fuzzy, the relic density for fuzzy dark matter or axions. It's the same class of models. And what all of these 5 kinds of mechanisms have in common is they're all about cold dark matter. I think Patty mentioned that warm dark matter was one of the possibilities in this wide range, and it was one that some people like for solving the apparent small-scale structure problems of cold dark matter, like the cusp core problem and the missing satellites problem, and that's because if the dark matter is warm, then it has a streaming length which could be big enough to wipe out the structures on those scales. But in recent years, Lyman alpha constraints have been making it more and more difficult for warm dark matter to be relevant. So you know, Lyman alpha is probing the structure of hydrogen gas clouds between us and distant quasars and showing how much power there is in the structure there, and seeing that, well, that power isn't getting erased at those scales, and therefore warm dark matter has to be heavier than, say, 4 keV, or it's debated, but it's getting to the point where it's difficult to invoke warm dark matter to get a big enough streaming length to wipe out those small scales of interest. So I'm just going to focus on cold dark matter today, and I'll start with a few remarks about the thermal freeze-out mechanism. So I believe one of them that wasn't mentioned by Patty, so if you want to find the relic density of your favorite model very accurately, you could download Micromega's software package or Dark SUSY. But suppose you don't want to do that. Then I think Patty didn't mention there is an analytic solution to the Boltzmann equation. It's an approximate analytic solution which works pretty well. It's described in Kolb and Turner. I meant to look up who originally did it. Somebody probably could remind me. But so he didn't show you this analytic thing, right? I'm not going to go through how it works. I'm just going to quote the result, and if you want to see the details, you can look it up in Kolb and Turner or in the appendix of one of my papers that's referenced for a slightly improved version. And it provides a formula for the present-day abundance of a dark matter particle as square root of 45 over pi g star, and a quantity x sub freeze out. So x was m over t. This is the value of m over t at the freeze out temperature, and I'll specify that in a moment. And then there's an integer n that I will define. And then we have the mass of the dark matter particle. And then we have the big Planck mass. So that's the 1.22 times 10 to the 19 GeV. And we have the thermally averaged cross-section where n is equal to 0 for S-wave annihilation, 1 for P-wave, etc. And sigma v, then you have to interpret this a little differently. If n is equal to 0, this is just the thermally averaged cross-section. But if n is equal to 1 or higher, then this is just some constant where you've taken the velocity dependence out, and the average velocity dependence is showing up in this thing. So x freeze out, so that's m over t at freeze out. That's also analytically determined to be logarithm of some other quantity minus yf minus half log of yf. And that yf is the number of degrees of freedom of the chi particle. So for instance, 2 if it's a Majorana fermion over 2 pi cubed, square root of 45 over 8g star. That's just coming from, well, the entropy density, I guess. And then we have m chi m Planck sigma v times n plus 1.
Two quick questions. One is the m in the xf, is that the dark matter mass?
Yes, so that I'm calling dark matter chi here.
Also, I've never seen someone take the log of a log that way. It's just not something I've encountered. That seems like an unusual scenario.
Yeah, and that's because the real equation is some transcendental equation, and you're solving it by iteration. So this is the leading approximation. That's the next to leading, and beyond that, you don't care because this is good enough. Okay. Yeah.
You said this was approximate solution. What assumptions are you need to make this valid?
Well, I mean, I think basically none. The approximation I just mentioned here is very unlikely to break down if yeah, because you start taking more logs, it gets to be a smaller and smaller. I'm sorry?
What's the small parameter?
Small. Yeah, no, there's nothing needs to be particularly small. Yeah.
Doesn't yf need to be greater than 1? If it's less than 1, you try and call the natural log of something smaller than 1, you'll get the natural log of a negative number.
Yeah. Okay. So that's a boundary of validity for this. So, yeah, if I had the time to actually go through the method, but that would take like half the lecture, then it would become apparent to you. So my purpose here is not to really explain it all, but just to make you aware that this exists, and you can look it up if you want more details. Yeah?
The sigma v in the first expression and the sigma v in the expression of y event, this is still talking about that, the coefficient.
Yeah, so really I should call this thing sigma naught, where it's a coefficient that appears in the thermally averaged cross-section. If I really need to thermally average, it's just for S wave, then they turn out to be the same. But again, see Kolben-Turner for the details. Now, there's another way of determining the relic density, which is even easier, and that is using the fact that you know that the cross-section that you need to get the right relic density is roughly independent of the dark matter mass. But people have worked out exactly what it is. And so there was a paper by Steigman and Beacom and company who did it earlier. I think this more recent one in the Dark Susie paper is more accurate. So there used to be, people would often use a rule of thumb. To get the right relic density, impose a canonical value for the cross-section, sigma v, of 3 times 10 to the minus 26. And so that would give you, a reasonable estimate. But if you want to do better, then depending on your dark matter mass, just match this cross-section. And that will give you a pretty good estimate of what you need for the right relic density. And I should mention that this is the right number for self-conjugate dark matter. So if it's Dirac dark matter, then you need to double this. Or if it's a complex scalar, you need to double it. And there's a easy way to understand that in terms of, if you think about dark matter particle, its relative density is being determined by its rate of annihilation on other dark matter particles. If it's a Dirac particle, then it can only interact with half of the dark matter particles in the bath. So the rate of interaction is going down by a factor of 2. You need to boost the cross-section accordingly in order to compensate for that. And let's see, so, yes, and another thing I wanted to mention. So Patty showed you the meaning of this thermal average. You just weight the initial state particles by the Maxwell-Boltzmann distribution and average over their momenta. But in many cases, it's not really necessary. And especially for simple S-wave annihilation, the cross-section is always going like a constant over V. And so sigma V is not very sensitive to the value of V for small velocities. And the velocity is relatively small when dark matter's freezing out, 0.3 or so. And so it's often sufficient to just omit doing this thermal average and just evaluate what this constant is. And that's very easy to do if you have, so if I have annihilation of dark matter, and I'll just label their momenta. So dark matter going into some lighter particles. And if you know the matrix element for that process, then you can easily work out that sigma times the relative velocity is matrix element squared over 32 pi mass of the dark matter squared. And then there's a phase space factor if the particles you're annihilating into aren't much lighter than the dark matter particles. And so then you just have to compute the matrix element at the threshold. So just take the dark matter particles to be annihilating at rest. And that gives a pretty good approximation. And of course, you have to multiply by a half if the final state particles are identical. Now, when would this be a bad approximation? So anytime when you have strong dependence of the cross-section on velocity, obviously. And so one situation where you must do the thermal averaging to get decent results is if you're near resonance. So an S-channel resonance. Suppose we had dark matter annihilating into the Higgs boson, and the dark matter is approximately half the mass of the Higgs. Then this intermediate propagator is going to go on shell, and you become very sensitive to how close are you to the pole of the propagator. So there, you better do the actual thermal average. And another place where obviously you have to do it is if it's not S wave. If it's P wave or higher, you should thermally average. But again, if you going back to the analytic approximation, here you can avoid this because this thing is actually just a coefficient which is related to the matrix element when you extract the velocity dependence, and the averaging over powers of velocity has already been done in this formula. It's giving you this exponent. So with this approximation, you can still avoid doing any thermal averaging integrals. Now, the other thing I wanted to say about thermal freeze-out concerns a different scenario than WIMPs. Yeah, maybe I should just, sorry, let me write this more explicitly. I have it in my notes. We can just write the actual expression. So this constant sigma naught is defined to be, it's defined such that sigma v so now I'm forgetting. Maybe you do have to do the thermal averaging to find that constant, but this is how it's defined. So the other example of thermal freeze-out, which doesn't fit into this scenario, is called strongly interacting massive particle. Are there some question about this first?
For modular and dark matter, we cannot use these thermal.
No, you can. It's fine.
For modular and dark matter.
There is no what?
No S wave, then you have to start from the P wave.
Oh, yeah, but I mean this, so I mean P wave is covered by that formalism. It's just the value of n. Yeah. So there's, beyond WIMPs, there's SIMPs, which means strongly interacting massive particle. And this is a situation where you don't have any annihilation channel into standard model particles. But instead, you could imagine that you have annihilation of 3 of the dark matter particles into 2. And so this would be most, so it's 3 to 2 annihilation occurring only in the dark sector. This would be most appropriate for a model like composite dark matter in a hidden sector where these things are pions and you've broken any discrete symmetry that would require just an even number in their scattering. So that's kind of a canonical example of this. But you can treat it in basically the same way as 2 to 2 annihilation. You just have to now brush up on what is a 3-body cross. What does it mean to have a cross-section with 3 particles in the initial state? And we're not used to thinking about it, of course, because it doesn't happen in colliders, but you can still define that quantity, and it's something that has different dimensions. But in any case, we could estimate what's the relic density in this situation in the same way as was done for WIMPs by the argument that the rate of annihilation, so imagine the rate of annihilation of a given dark matter particle, it's going to depend on the densities of the 2 others, and therefore we get an n squared instead of just n, as per the usual formula. And that equation shows you how the dimensionality for a 3 to 2 cross-section differs. It has to go like 1 over mass to the 5th in order to absorb the extra density. And so, as usual, one equates this to the decay rate at a temperature which is of order the mass of the particle. Realistically, it should be somewhat lower, maybe a factor of 10 or 20, because we've seen that freeze-out always happens not right at the particle mass, but somewhat below it. But just for a parametric estimate, that would give us something of order m squared over m Planck. And so then when you equate these, you can solve for the Rayleigh density of the dark matter, and it has a different dependence. Instead of going like 1 over the cross-section, it goes like 1 over the square root of the cross-section. Now, interestingly, let's see. Did I get this right? So that would mean that the energy density, m times n, so that would go like m squared over. Let's imagine that we're in some hidden sector where there's just one mass scale. Like in QCD, the relevant mass scale is the confinement scale. And so let's call that mass scale m, and then we would imagine that sigma v goes like 1 over m to the 5th. Yes, okay. So then you can set this equal to the observed relic density and get an estimate for the mass scale. And you find through this simple estimate something of order of GeV. When you do it more carefully, turns out to be smaller, say 100 MeV or less. But anyway, this is showing you that in this scenario, you expect that the dark matter is going to be naturally lighter than in the WIMP scenario. Just to get...
1 over m sub 5, and I can't tell if that's supposed to be the dark matter mass.
That was supposed to be an exponent. Thanks.
Dark matter mass or the Planck mass?
This is the dark matter mass again. Okay, so that's all I wanted to say about thermal relics. And next I would like to mention an important non-thermal mechanism, which is asymmetric dark matter. And I won't have a lot to say about it. It's like the baryon asymmetry. We don't know what the origin of baryons are. It could well be that dark matter also has some conserved number, and it's arising from an asymmetry, like the baryons. We have lots of ideas how that could happen, but very little evidence about what's the most likely mechanism. So I'm not even going to speculate about mechanisms. I'll just assume that chi has a conserved particle number. And by some means, it gets an asymmetry. So we could then talk about the two different components of the dark matter. There's the dominant one, which would be, so let me talk about the asymmetric one as being the dominant one. So it'll be the max of whatever is most prevalent, the dark matter or its antiparticle. And then there will typically be a non-negligible amount of the other kind. Unless, of course, the annihilation, so you want there to be an annihilation of chi bar into standard model particles typically. Because, and you want this to be, you want this to have a big cross section. It should have a large cross section because otherwise there's no reason to expect that this symmetric component is going to be much smaller than the asymmetric component, and then you're back to thermal dark matter. In other words, typically this particle will have had a thermal origin, and we just want to suppress its relic thermal density so that that's a negligible contribution in order to make this asymmetric mechanism relevant. Okay, so that's the assumption, and therefore we know that this sigma v for this process is much greater than the standard. So that's the standard value that we needed, which is of order 3 times 10 to the minus 26 centimeter cubed per second.
How do you have a conserved particle number if you have annihilation?
Because a particle can always annihilate with its antiparticle. That doesn't violate conservation of the particle. It's just, so we have baryons and antibaryons.
Oh, right, yeah.
It's just that there's no process that will change. So we haven't changed chi number here. We started with chi number 0 and ended with, yeah. Now, I just want to point out one possible conceptual error that you might be tempted to make when you're thinking about these kind of scenarios, because of this statement that, so unless, well, I'm going to show you. So the question is, how big does this have to be in order to make the symmetric component completely irrelevant? And the relevance, of course, of this symmetric component is that if we have these kind of processes still going on today, these can lead to indirect detection. And you'll have lectures on that a little later on. And so it's interesting to know, well, how big does this cross-section have to be in order to make it unlikely for us to be able to see this in the present day? And a naive estimate would be the rate of indirect events will just be suppressed by the ratio of these two things, because, of course, in the standard thermal freeze-out, you know that the relic density is just going to go as the inverse of the cross-section. So you might think that is, okay, it's just going to be a proportionality, but that's not true. And the reason it's not true is because as we make this bigger and bigger, at some point, the asymmetric component becomes important. And it doesn't go away. It stays the same no matter how big you make this. So it means that even if this is very big, a dark matter antiparticle, suppose that's the one that is less likely, it can still find a dark matter particle much more easily than it could have if it was just purely thermal dark matter. And that means that indirect detection is suppressed much faster as a function of this than that naive reasoning would have led you to believe. And so this was all worked out in a nice paper by Gresser et al., where they show you precisely what is the ratio of the subdominant component so the symmetric to the asymmetric component in my language. What is that ratio as a function of this ratio of cross sections? So the actual cross section versus the standard value. And you see the answer here. It's going down exponentially. It's not just a power inverse power of this, but it's exponential. And this leads to a very quick suppression of the signals from indirect detection.
One question, what is RUP?
It's just this. It's the ratio of the two abundances, current ratio.
If you have a large cross-section, doesn't that mean you should also have an increased chance of going, of the inverse reaction, so like annihilating to produce dark matter, anti-dark matter pair?
Not once you get below the mass of the dark matter.
How massive is the dark matter we're talking about?
Well, so you're talking about the inverse scattering?
Yeah.
No, that's Boltzmann suppressed. So as soon as, these are assumed to be much lighter than chi. So as soon as you get to temperatures such that much below the mass of the chi, then that's exponentially suppressed. Because these things, they have energies of order of the temperature.
I guess my question is, wouldn't that make it easier to find it in a particle accelerator?
Oh, I see, through the inverse
Yeah.
process. Yeah, I mean, usually people like annihilation into B quarks in all of these indirect detection papers. So if you had a B quark collider, then you might have good chances. Well, I'm being facetious, but let's see. And interestingly, how am I doing on time? So interestingly, to avoid bounds from the cosmic microwave background, that imposes a lower limit on this cross-section. So that's a little novel. Usually, we're used to thinking of getting upper limits on cross-sections from indirect detection. But for the CMB, we want to suppress this through this exponential penalty, so we need a bigger cross-section. And the CMB limit is that sigma v has to be greater than about 10 to the minus 25 centimeter cubed per second for 10 GeV dark matter, or somewhat bigger, 7 times bigger, for one MeV dark matter particle. That's from Zurich and Company. You can find references in my notes, which are online. Another way of constraining asymmetric dark matter, if it's bosonic, it likes to accumulate in the cores of black holes. And so if you get enough of them, that will cause collapse of the black hole. And so that puts a limit on the cross-section of dark matter with on nucleons, because we need scattering of dark matter on nucleons to get trapping in neutron stars. And so neutron stars give an interesting limit on the chi nucleon cross-section. So it gets, let's see, so less than 10 to the minus 47 centimeters squared for dark matter in the range of few MeV to 15 GeV. It's another Catherine Zurich paper. She's the queen of asymmetric dark matter. And of course, that's interesting because that's in a region that's very difficult for underground direct detection experiments to probe. Okay, so that's all I wanted to say about asymmetric dark matter. And now I'd like to talk about freeze-in. And this is this concept was introduced by Hall, Jadamzik, March, Russell, and West in 2009. The idea was, unlike thermal freeze-out, imagine that you had a dark matter candidate that never came into thermal equilibrium. So suppose that it was not produced during inflation and very inefficiently produced by interactions. So we're talking about dark matter that is generally very weakly interacting, more so than WIMPs. And so its actual density is starting out much smaller than the equilibrium density. In that case, the Boltzmann equation simplifies, and we'll just write down the terms that only involve the equilibrium density. So the general form is x times the entropy density times the cross section divided by the Hubble parameter at the temperature equal to the mass of the particle. So normally this would be y equilibrium squared minus y squared. But we're saying that y, the actual abundance, is much smaller. And so we can make the approximation that it's just this. And then the Boltzmann equation becomes much easier to solve because nothing depends on y on this side. We can just directly integrate it.
Because it was the H approximately at freeze out. So why do we still have that term if we no longer have a freeze out?
It's let's see. Where is it? Where does it come in the?
I think it's just because it's a convenient parameterization, and you know how Hubble scales. It doesn't actually matter about freeze out.
Yeah, that's true. I'm sorry?
All of the temperature dependence is constant x.
Yeah. I was just trying to remember when you originally derived this equation, where was the h coming from? Yeah, but oh, I remember why. Yeah, it's because we've traded time for, yeah. So remember, the original equation was in terms of T, but T is related to temperature through the Hubble parameter. So it's just the constants that appear when you change from T to X. You know, there's a Jacobian, and it's just the constants that appear in that change of variables. But now, so when you look at this equation, the solution to this equation, what you find is that, okay, so then you just do the integral. So you say that y chi is equal to the integral dx of this stuff. And what you find is that this is going like dx x squared times this modified Bessel function that's appearing in the definition of the equilibrium density. And you find that this is dominated by small x. Which is high temperature. And that's unlike the thermal freeze-out, where you know that everything's being dominated by the contributions near the freeze-out temperature. So that means that you have to be careful about what you use for sigma v here. You shouldn't use the low temperature limit. You should use the high temperature behavior of sigma v to do this correctly. And typically, that's going to be suppressed just by dimensional analysis. You expect that sigma v is going to go like 1 over temperature squared at high temperature. So it would be something of order lambda squared over t squared because this propagator is getting small at high temperature. And we can write this as, sorry, that should be lambda to the fourth. So we can write that as lambda to the fourth x squared over mass of the dark matter squared.
It's high temperature of the, universe, or high
Yeah.
temperature of the dark matter?
We never talk about the temperature of the dark matter in all of this.
Okay.
We don't care about its, we're using temperature as a way of keeping track of time and, and temperature of the part of the universe that's in thermal equilibrium. So now you can just plug this in and do the integral, and you find that m chi times its equilibrium density is of order 10 to the minus 4 lambda to the fourth m Planck. And if you compare this to the critical density expressed in, if you compare this to what you need using the critical density, this is what you need, then you can solve for lambda and find that it's of order 10 to the minus 6. So that's illustrating to you this statement that we're talking about dark matter that's very weakly interacting here. So, yes?
Am I right in thinking that that statement that this production is dominated by the high temperature limit assumes that all of the initial and final state particles are fermions?
Oh, you're saying I could get around this if I was
If you're
using
saying they were scalars, then it would be
just a phi to the fourth interaction.
I wouldn't expect it to care about high temperature.
Yeah, so I guess maybe, yeah. So I've assumed something here. I haven't tried to analyze it for all possible cases. Let's see. Well, actually, so this, though, this wasn't taking into account any dependence on sigma v. So, for instance, if sigma v was constant, I think this statement would still be true.
In what sense do we need, so like you say, we need this to the value of m times the equilibrium density to be equal to this? If it's
This is not equilibrium density. This is the current density. This is what you get from doing this calculation.
all right, so-
Yeah. Yeah, so you might want to check how does this argument change if you have bosonic with a contact interaction. It's just interesting that if you tried to do thermal freeze out with such a large value, you would need a very low dark matter mass. So with thermal freeze out, sorry if this is too low to see, such a weak interaction would imply a dark matter mass of order 0.1 eV. Anyway, it's just a very different regime from freeze out. I will mention one other. Here, I'll trade these boards. I'll mention one other example that's come up recently. I think it's interesting because the nightmare scenario for dark matter, it doesn't interact with anything, except it always interacts gravitationally. And so it's interesting that you can have freeze-in to give the right relic abundance even for particles that interact only gravitationally. And this was pointed out in some papers from 2015 and 2017 by Martin Sloth and collaborators. And that's an example where the temperature dependence is different. So gravitational interactions only. Then we would have exchange of a graviton here. But we know the scaling is going to be different because it's non-renormalizable, and these vertices come with powers of the energy and the momentum and inverse powers of the Planck mass. So in that case, we know that sigma v is actually going to scale with positive powers of the temperature. Let's see. But obviously, it's still the case that the integral is going to be dominated by the high temperature contributions. So that statement doesn't change. And what these authors estimate is that you can have dark matter with masses as high as 10 to the 16 GeV. That's the upper limit they find. Of course, you may still ask, well, who cares, because we'll never be able to see that dark matter. But these authors at least point out one possibility, and that is we often invoke global symmetries to ensure this or explain the stability of dark matter. And yet we believe that quantum gravity doesn't respect global symmetries, and that quantum black holes would make such dark matter, or gravitational instantons might make such dark matter particles unstable. And so these authors discuss the possibility that such gravitational effects might lead to slow decays of dark matter into standard model particles due to quantum gravity effects. So perhaps it's not hopeless to see dark matter even in the nightmare scenario. And that's all I want to say about freeze-in. The next thing on my list was primordial black holes, which have gained interest recently because of the LIGO observations. LIGO seeing events indicating that maybe there's more 30 solar mass-ish black holes out there than one would have expected. And so we'll use this as a target mass, because it's known to be, that's one of the windows that's not excluded by macho searches and other constraints on primordial black holes. And many astronomers are fond of this scenario because they say, oh, this requires no new physics. It seems like a very conservative dark matter candidate. But what they fail to realize is that in order to produce these things at the needed relic density, you really do need new physics. And so that's the part I want to just mention to you right now. And so the way you would relate this, well, black hole of a certain mass, yes?
Have these guys be the entirety of dark matter? I mean, I know that there's bands with that mass.
In principle, they could be, yeah. And, well, the way you would imagine getting getting primordial black holes of a given mass is you would need a very rare density fluctuation coming from inflation. This in ordinary inflation, the density perturbation is a Gaussian variable. So this is some Gaussian random field. And that statement is true mode by mode in Fourier expansion. And so you would need some rare upward fluctuation of that. You would need it to be of order 1 in order to produce a black hole. So you need a big fluctuation. And the mass that you would produce would be basically the amount of mass contained in a region whose wavelength corresponds to this k number. So that would give a mass which is of order the critical density times the wavelength cubed or divided by k cubed. And so if you just take the spectrum, the power spectrum for this that we've deduced from inflation, of course, from inflation we don't deduce it, and this defines a particular scale. If I want a 30 solar mass black hole, that tells me what wave number I need to be concerned with. And those are very short wavelengths that we don't probe directly from the CMB. But if we assume that the power of those fluctuations was the same at those wavelengths as what we measure in the CMB, then we would find that this kind of fluctuation it's just impossible. It's super exponentially suppressed. And what it means, therefore, is that we need to have a boost in the power on those scales compared to what we measure in inflation. And I won't draw that because I have this nice picture from a paper by Bringman et al. There's my stick. And this is a picture of constraints on black holes where we have the wave number going from 10 to the minus 3 to 10 to the 19th inverse megaparsecs on the bottom, and the scalar power spectrum on the top. So these are the wave numbers measured by the CMB, and this is the magnitude of the power at those scales from Kobe. This line is showing you what you would need in order to get primordial black holes at the observed relic density. And some of these regions are excluded. So Macho searches and Lyman alpha exclude this range of black holes. The ones that LIGO sees are here. And I think Macho searches, I forget. So there are a bunch of different constraints which are ruling out some of these regions. But the main point to take home here, even though this is allowed, it's showing you that you would need a huge increase in the power from these scales to these scales. It's not just going to be some simple power law probably that's accounting for that. And it is possible. So one way to do that is to have a step potential during inflation. And so if you imagine that the inflaton potential for some reason had a discontinuity, then it's not too difficult, and it's left as an exercise in the problem set I put online to show that you get a big boost in power right at the scales that correspond to horizon crossing of these modes. And so that would be a way of producing a spike in the power where you want it. And it turns out to get a big enough spike, and this is also part of the exercise, that you need the step to change the potential by a factor of order 10. I mean, what you really need quantitatively, though, it's extremely fine-tuned, because all of this is going into a Gaussian probability distribution function for delta rho over rho. And so any little change here is exponentially amplified. And so to get just the right amount of power on that scale, you really have to have this tuned carefully. And so you see there's two contrived things going on here, this special feature in the potential and also exactly how big the drop is. Yes?
That looks like it represents a spectacular violation of slow roll. What does that not mean that like all of you?
Well, it's rolling slowly here, and then, well, it picks up a little speed there, but it also quickly Hubble damps when it gets down here. So you can join the two slow roll solutions onto each other, and that's part of the problem, is to show how to do that matching.
Discontinuity in your derivatives as well, or do you not boundary condition patch them across so you don't have a step function in your B prime, for example?
No, the slow roll equation is a first order equation, and no, I forget. The details are all in that exercise. I'll let you. There's a question.
I was just wondering, so the minimum is at pi equals 0? So I'm a little confused about how inflation would work.
Oh, this is just a part of inflation that we don't even observe, and the part that we do observe is happening somewhere later on.
Can we get multiple discontinuities to side by side that will amplify it, so can we get rid of the fine-tuning?
Through multiple discontinuities?
Yeah.
I don't see how it would get rid of the fine-tuning. It would give you several spikes at different wave numbers. Yeah. No, I was. Well, what I'm saying is that the actual power that you get out is exponentially sensitive to how big the jump is. Whether it's discontinuous or not, I think it's still going to be rather fine-tuned. Yeah.
So I feel like I remember hearing that there's a minimum mass for primordial black hole, dark matter things from like evaporation. Like if the primordial black holes were smaller than a certain mass, then you'd have like they would evaporate due to Hawking radiation
Right.
too quickly, and then you wouldn't still see them. But there's no lower bound on this that I see. Is this just not represented on here?
I don't know. Maybe that's where the line ends.
Well, that's increasing mass.
Oh, you're right. You're right. Okay. No, I don't know about that. Yeah.
That's a problem, like how sharp the drop would be. Like, would that flatten a little bit? Like, say, if it happens in a certain width, then would that greatly damp the spike that generated?
I don't know if it would damp it. It would spread it out. I don't know. I've never done this calculation.
Can black holes eat photons?
Sure. Black holes can eat anything. Anyway, my take on this is that it's possible to make it work, but it seems like several unlikely things are going on here. So the final possibility I want to mention is the fuzzy dark matter or axion-like particles. And I think this doesn't overlap with Anton Hook's coming lectures because I don't believe he was going to talk too much about the origin of the relic density. So Patty did mention fuzzy dark matter, and these are really just another regime of axions, not the QCD axion, but a more general axion-like particle, where one takes the potential. Well, let me show a picture of the potential. So this is supposed to be a tilted Mexican hat potential. And if Pachequin symmetry was not broken, then it wouldn't be tilted. It would be an exact symmetry, and the axion would be a true Goldstone boson. So we're interested here in, yeah, for my purposes, the tilt, wait a minute. Yeah, the tilt is still important, obviously. We need the axion to get a mass. So it's convenient to parameterize it. Since you see it's running around, it's living on a circle, it's convenient to think of it as being a dimensionless angular variable. And I'll just follow Witten and company and call it A. And the effect of this tilt in the potential is just a cosine kind of potential. We have two scales here. So there's a scale F that's known as the decay constant of the axion. And then there's another scale here which is associated with this breaking effect, the lifting of the potential. And you can easily see, you can work out by expanding in A that the axion mass is just lambda to the lambda squared over F. And I guess it's already been stated, but in the case of QCD, we're usually interested in masses in the range of 10 to the minus 6 to 10 to the minus 2 EV. But the possibility of dark matter being much lighter than that, down to 10 to the 22 minus EV, that was emphasized by this paper by Witten et al., Hui, Ostreicher, Tremaine, and Witten in 2016. Actually, that wasn't the first. There was an earlier paper by Hu, Barkana, and Gruzanov back in 2000 that was, I think, the first to suggest this much lower mass scale of 10 to the minus 22 EV that's identified with fuzzy dark matter. And Patty already mentioned the motivation for that scale. It's that the de Broglie wavelength of the particle then becomes of order kiloparsec. So 1 over m, I guess, is of order kiloparsec. And so it means that with this kind of dark matter, you cannot form structures on smaller scales. And so that would be good for this cusp core problem. Yeah. The lambda?
No, the theta, the cosine theta.
Oh, that's A. I'm just calling the field A instead of theta.
So A is the axial field.
Yeah. in a dimensionless form. Because I've expressed it as a dimensionless quantity. But if you prefer, the way people usually normalize it is to absorb the F into the A here and then divide right A over F there. It's just a notation. So the part I want to talk about in this lecture is how the Rayleigh density comes about. And so probably many of you are already familiar with this misalignment mechanism.
Start having like weird superfluid type properties?
Yeah, in fact, that's one of the interesting things about this is that you can have Bose-Einstein condensation. So that's part of the whole study of this kind of dark matter. And it's also part of the controversy about axions, whether you can have Bose-Einstein condensation for QCD axions. There's some debate in the literature on that subject. So I want to talk about the misalignment mechanism. And it's very simple. The idea is that you started out in the early universe at temperatures such that the tiny energy difference between the true vacuum and other places on the vacuum manifold is just irrelevant. And so you can just easily populate by random chance any place on this vacuum manifold and find yourself in a universe, because there'll be fluctuations of the axion field, and you'll find yourself after inflation in a region where the field is just taking a random value. So during inflation, just like any other massless field, the axion field is going to have fluctuations of order h. And if h is large enough, well, actually it doesn't matter because the origin of the axion field is kind of irrelevant at these scales. So everywhere on that vacuum manifold is going to get populated. And at the end of inflation, we expect that these regions with different values have gotten blown up to encompass our horizon. And we'll just have an initial value of the axion field that is anywhere. So, and during the early, as long as, even after inflation, as long as the mass of the axion is less than the Hubble parameter, it remains frozen. So the universe is cooling. The axion is evolving very slowly, so that it's approximately frozen. But as soon as we reach the point when they're equal, then it starts to budge. It starts oscillating around its minimum. And one can show that an oscillating coherent field like that starts to just redshift like dark matter. And so, putting those statements together, we can easily estimate what's the energy density of the axion today. So, let's see. So initially, the energy density of the axion was just due to this lambda to the fourth potential. So it's of order lambda to the fourth. And it stays that way until it reaches this oscillatory phase. And then it starts redshifting. So so after m equals h, we have that rho is going as rho initial, and then it goes down like a cubed. So a initial over a cubed. And in particular, the current value of rho will go like this. And now we can just replace these with temperatures. So that'll be T naught over T initial cubed. So that's the density today. And we also know what T initial is because it's coming from, I don't want T initial here. I want the epoch when it starts oscillating. Let's call it OSC. Because it didn't start redshifting until then. But we know what that is because it's when the mass of the field is of order the temperature squared over m Planck. So we have everything that, we have everything that we need. And you can then easily show that the so the relative contribution to the density of the universe, dividing by the critical density, turns out to be of order 0.3 times the mass of the particle to the 1/2 and f squared divided by some benchmark values. So for fuzzy dark matter, one would like to think of the mass as being of order 10 to the minus 22 eV, and that tells you then you want the decay constant to be around 10 to the 16 GeV. Or I could rearrange the numbers and write a mass more appropriate for axions, say 10 to the minus 3 electron volts. And then that would tell me that I want a decay constant closer to 10 to the 12 GeV. So I should put one caveat. So this whole misalignment mechanism, there's an underlying assumption here. It assumes that the shift symmetry of the axion, whatever you want to call it, for the case of QCD axion, it's the Pache-Quinn symmetry. That symmetry was already broken at a very high scale above inflation, or during inflation. Because we're assuming that we had this, that there was no phase transition. But that doesn't have to be the case. And in particular, for the QCD axion, it could be that there's a phase transition happening after inflation, which we would call the Pache-Quinn phase transition. And that's where this lambda potential, initially it's 0, but it suddenly appears due to some strong dynamics. In the case of the axion, it's QCD instantons. And I just want to mention that if the symmetry breaks at a lower scale, then you can get additional contributions to the axion density because you're going to be able to form cosmic strings where the axion field is winding around. So you can get cosmic strings. And in some axion models, you can also get domain walls that are connected by the cosmic strings. And anyway, the decay of the strings leads to extra contributions to the thermal axion, to the axion particles. And so this increases the density relative to the estimate that we've made here. And so that's an important uncertainty in trying to understand quantitatively the relic density of axions today. And to do it properly, it requires numerical simulations of axion string networks, just like people do cosmic string simulations or have in the past.
MA goes to 0, so it's always going to be less than H, and it stays frozen. It looks like what you got is effectively burned energy, and that's the only thing where rho I just does not depend on your scale.
Sorry, I didn't get that.
Before it starts oscillating, when it's still frozen.
Yeah.
Rho I is about.
Oh, you're saying, yeah, it looks like dark. Yeah, well, it is. It's just, that's all it is. It's just a potential. It's like a little inflaton, but it's not dominating the energy density. Yeah.
I think here there's also hidden assumption that the axion-like particle get a mass right after phase transition.
Yeah. Yeah. So one should probably be careful for particular model to be sure that. No, but I think the temperature dependence of the axion mass is such that it very rapidly goes to 0 when you're close to that phase transition.
Yeah, I think there are two phase transition. One is a Baryogenesis symmetry phase transition.
Ah,
the other
is the
non-perturbative one.
I see, the QCD.
Yeah.
I see.
So
Okay.
axion will not get a mass around QC, before QCD.
Yeah. Okay, so one should be careful about the real temperature dependence of the axion mass. Yeah.
Here, this is showing that the symmetry makes during inflation, or is it before inflation?
In all of this, I was saying this was the assumption.
Why do we need this assumption? If this is not true, then this is
If it's not true, then this potential, this lambda to the 4 potential, just isn't there yet. It only arises after the symmetry breaking.
no, I mean, why the symmetry has to break during inflation and why
Well, or before. It doesn't have to be during. If it's after, then we're in this situation where you have cosmic string networks, and then this is an extra contribution that wasn't taken into account here. Because you're producing big coherent objects which eventually are going to decay and give you extra contributions to the dark matter density. Okay, well, I guess I'm done, and it's been a pleasure interacting with you, and thanks for all your nice questions.